Hi there. This is an introductory video in a series that will allow you to explore the world of digital circuit design. This series will be of particular interest to those who have enrolled in the VLSI courses at the university, or anyone who just wants to play with electronics. We'll begin the series by looking into what a transistor is, the fundamental building block of digital circuits, and unlike analog circuits in which we use inductors and capacitors, in digital circuits, we only use one element, the transistor. So it's going to be much easier than you think. In short, a transistor is a variable resistance device. It's a device that can act as a resistor or a conductor, and we can use it as a switch or an amplifier. Let's have a look in a circuit and see how a transistor behaves. What we see here is a transistor in a circuit with a battery and an LED. Transistors come in all sorts of sizes depending on the amount of current or power that we want to control. Here's for example a tiny one compared to the fairly bulky one we're using. You can find transistors as tiny as a few atoms in a processor. In our circuit, two of our transistor pins are attached to the circuit it controls. The transistor is controlled itself by a third pin which is left unconnected at the moment. The transistor is obviously at its off state at the moment, and hence the continuity of the circuit is broken at this part. Electricity cannot flow and the LED is turned off. This is an N-type transistor, which means if I touch the transistor's controlling pin to the negative side of the battery, it turns off, whereas if I touch the pin to the positive, it turns on. We'll discuss what N and P types are in a moment. Let's see this in action. I'm going to simply touch the battery's positive terminal and the controlling pin of the transistor. We see the transistor turns on. The key note here is that the transistor is so sensitive that one can turn it on or off simply by touching the pin. Note also that I can touch directly the controlling pin to the negative and positive terminals and no resistor is required. There are two main different types of transistors, one being the bipolar ones, which is version 1, and the other is the field effect transistor, which is version 2, and are the transistors we are going to be using. The initial idea was to develop the field effect transistor, but it was quite difficult at the time, and they ended up with the bipolar ones. Sometimes the initial idea is just the better one. The bipolar transistors are effectively two diodes which are connected in reverse, and therefore they do not allow current to travel in either direction, except when we disable one of the diodes by forward biasing it, that is, passing current through the direction it requires. The problem with bipolar transistors is that they require a constant current supply in order for them to be turned on. They also develop a voltage drop of 0.65 volts across the circuit they are connected to, greatly reducing the efficiency of the circuit, especially when we are dealing with digital circuit design and 3 to 5 volts. Imagine, for example, having to develop a computer processor where we have millions of transistors on a die. It would require a whole power plant for it to work. I suggest you never use them. The field effect transistors, on the other hand, do not have the problems the bipolar ones have. Let's see how they work. In the last circuit we saw, we used a field effect transistor. We will draw the schematic equivalents next to each element used. So this is a battery. This is an LED. And since we will build upon the transistor, we will start with a gap in our circuit. Okay, now we'll fill this gap with an insulator, let's say a rock. An insulator is a material that does not allow current to flow through it, as all its electrons, the charge carriers, are trapped in bonds between atoms.
Bill Shockley, the inventor of the transistor, reasoned that although the electrons are trapped within the valence band of the material and cannot move, there still are some electrons in there. So how can one attract the electrons and liberate them out of the atoms? Well, you guessed it, by electrostatic forces. We can attract those electrons with positive charges, which is a lack of electrons. Putting a positively biased plate on top of our material, we can attract our electrons, which form a conductive layer on the top side. This is the conductive channel, and this is when the transistor is on. To really understand what a conductor or an insulator is, we have to understand how atoms behave in a solid crystal lattice. Recall from high school where we have a single atom. Its electrons can reside in one of the stable orbitals around it. When we bring two atoms together in a solid, let's say like this, the higher orbitals merge into a single band, which we call, this is the conduction band and this is the valence band. In this band, the electrons cannot move within the solid, and in this band they can freely move around. To liberate an electron from the conduction band, from the valence band to the conduction band, we need some energy, and this is called the energy gap of our material. What we just drew here is an N-channel enhancement mode MOSFET. This is its gate, this is its source, and this is its drain. To see the symbol is, you have to draw it like this in digital electronics. This is the source, this is the drain, and this is the gate. There are also depletion mode MOSFETs, which normally are turned on, and they need some charge to turn them off, but we will not deal with them. The enhancement mode transistors come in two flavors, which is the N-type that we just saw and the P-type. The N-type is symbolized like this, and the P-type is symbolized like this. It has a small circle around here in the gate. The N-type transistor needs a minus on its source, a plus on its drain, and to turn it on you need a plus on its gate. The P-type does exactly the opposite. It requires a plus here, a minus here, and it requires a minus here to turn it on compared to its source terminal. So now we hopefully understand what a transistor is and how it works. In the next video we'll see how to put them together to form a simple NOT gate, which is the basis of all CMOS logic design. Until then, thanks for watching, and we'll see you soon. Imagine, for example, trying to develop a computer processor when there is 1 million processors, excuse me, transistor inflation, 100 million processors on the die